Sorry, I also have to add, this is our setup from the lab. I needed to get that in for the points. I did a lot of this through simulation, but in person, this is what we got, and this is our setup. Thank you. This is Landon Hicks Lab 4 with circuits. Okay, let's get into it. Introduction and background. We're going to use multimeters to measure the current potential. We're going to predict circuit behavior in a series of parallel resistors and ammeters and voltmeters. Explore resistor and capacitor behavior. All right. Necessary principles. We're going to be using node rule, meaning that if current goes into one spot, it needs the same amount of current has to go out of the same spot, right? Loop rule, meaning that if I have something in a loop, the total electric potential must sum to zero. We're going to be using that a lot in this lab. And then Ohm's law, we got V equals IR, and manipulating that equation to get what we want at any instant, right? All right, so let's look at first. They give us this graphic, right? And so predict currents I1 and I2. That would be measured by the ammeters. Ammeters have very low resistance. We're not going to take in those resistance. So our total resistance is going to just be those two resistors added up, so 147 ohms. And we're going to end up getting about 0.02 amperes, all right, using the Ohm's law. All right, so do the simulated currents match? Yes, they do. They're about 0.02 amperes. So when we're simulating it, everything matched up. So what happens if we reverse the connections to our amperes? Nothing. These calculations were done with the total resistance and the I is constant throughout the circuit. It sums to zero, so it's the same charge through it. All right. So what happens if we replace the ammeter with a voltmeter, right? So the other ammeter may read zero because the resistance is very high in the voltmeter, and so yeah, it's just going to take all the charge. The entire 3 volts that comes through those two batteries is going to deposit into this voltmeter, right? And that's why it reads 3 volts. All right, so what is the voltage drop across each part of the circuit? All right, so we use the loop rule to see this. We have our volts, our IR47, IR100, this is for our resistors, and for our capacitor, for our battery, I guess. And then, okay, so we have 3 volts going through the battery. We got, when we use IR, we do the current that we calculated times the resistance. We're going to get 0.96 volts and 2.04 volts. We know when it goes through these resistors, it's going to go from from positive to negative, making it negative and making it sum to zero throughout the entire thing, right? And everything else that's not a resistor or a battery will be zero. And we're assuming that this has a resistance of zero, and therefore I times R would be zero. Okay, visualization of voltage drop throughout a circuit. All right, so you're going to see it increases in the battery. When we're looking at this battery, it increases very steeply. That's going to be where our 3 volts comes from. Throughout wires that are not resistors, it stays constant because the resistance is zero. When you get to the resistors, the slope is based on the resistance. So you can see at the 47 resistor, it's a little bit shallower. At the 100, it's a little bit steeper. Right? Why does the ammeter not change? The voltmeter has a very high resistance, dropping the voltage close to zero to the resistors in the graph with much steeper slope. The voltmeter, it's an incredibly high resistance. It's just going to go straight down, right, and get to zero before it even reaches the ammeter. Right. So I'm going to replace one of the ammeters with a 100 ohm resistor, right? The ammeter how much resistance. It's going to want the path of least resistance. It's going to go through that, and it's going to basically take out that 100 ohm resistance, and we're going to have 47 ohms as our new resistance. That's going to give us an I of 0.06. All right, what is the resistance of each circuit element? All right, so we have R equals the I. Okay, so essentially we look at the resistance based on the amp meters and the volts that we had. Uh, we had gotten, now this is the rounding error. As you saw, like it wasn't exactly 0.02. It was a little bit above that. So these are just rounding errors. So they're approximately the numbers that we see in the simulation. 48 is close to 47, 100 is close to 102. And we know that it's zero throughout the one and zero. I said that was basic. So, the stopwatch, it was basically ohms per second. So 10 ohms, you get 10 seconds, 20 ohms, 20 seconds, 27 to 50 seconds. RC circuits. I'm going to set up a 9 volt battery, 200 millifarad capacitor, and 30 ohm volt connected in series. So you're going to see it has this downward linear slope. Our predicted resistance of capacitor was 30 ohms times 0.2 farads equaling 6. And then our experiment, we did that over the slope. So that is the slope that you see there, 0.1453. One of that means we saw that was a resistance. And that's going to be about 6.88. That's approximately the same. I'm not too worried about the potential air. This was done in person by humans. They time. We time how long it took to discharge and charge, and that's by human calculation, so it's kind of hard. Online simulations were idealized versions as well, so they failed to take into account like confounding variables that would make it something more realistic. And so what if we were to do this in real life and use an ammeter or instead of an ideal simulated ammeter? All right, so actual ammeters do have resistance. The one in there had absolutely zero. That's one of those confounding variables. While it is a low resistance, it will have some. So it won't be perfect that the eye was in this simulation. All right, so if you were doing this lab in real life and used a real battery to charge a capacitor with no resistor, how quickly would it charge? If it was an idealized battery with no resistance, instantly. If there's no resistance, I was going to go through there instantaneously, basically. But in real life, batteries do have resistance, so this charge will take time, and that resistance will be what determines how much time it takes. Make sure your time.